Hey everyone, welcome back to another Watch Me Do Math video. In this video, I'm going to be going through another step question from the 1987 Specimen paper for the Step 1 exam, which is currently defunct, but still serves as a good training ground for the harder Step 2 and Step 3 exams. So, in this video answer, I'm going to be explaining how you can get from the question here to a solid answer, and hopefully, if you are viewing this for the purposes of your own education and training, you'll find this helpful, and you may be able to share this with anyone else who might have a need for it. So let's begin. In the figure, the angle PAC is a right angle. AB is H, BC is D, AP is X, and the angle BPC is theta. Express tan theta in terms of H, D, and X. Right, so the way that I approached this the first time I saw it was that I was trying to find the tangent of this angle, not through any geometric means like plotting some line here or whatever, but in fact to do it through algebraic means. Because I realized that the tan of this angle here, let's call it alpha, which encompasses A, P, and C, would be easy to find, and I realized that this angle, the tangent of this angle beta, would be easy to find. And if I knew tan alpha and tan beta, then because theta was alpha minus beta, I could use the compound angle identities I knew for the tan function in order to find a value for tan theta. And in the second part, the process is also fairly straightforward. You would differentiate the expression you have for tan theta with respect to x and find the x at which it was equal to 0. And do a little bit of extra justification to show that it was truly a maximum value you were looking at. So, firstly, we know from basic stuff about right-angled triangles, if we let beta be equal to the angle APB and alpha be equal to angle APC, then tan beta is opposite over adjacent is h over x, and tan alpha is opposite over adjacent is h plus d over x. And because alpha minus beta is theta, as I mentioned before, tan theta is tan alpha minus beta, which is tan alpha minus tan beta over 1 plus tan alpha tan beta. Or I believe this is the actual formula. I'll just quickly check against my answer that I've done already, and yep, that's correct. So if tan theta is that expression over there, we can substitute what we know about tan alpha and tan beta to get an expression in terms of h, d, and x. So this is h over x minus h plus d over x over 1 plus h times h plus d over x squared. If you multiply the two fractions together, that's what you get in your head. So this is tan alpha minus tan beta. So that it should be h plus d on this side minus h on this side. Yep. Okay. So to simplify this further, you get h plus d minus h is just d over x over, well, 1 is x squared over x squared plus h times h plus d over x squared. And to merge the two fractions in the bottom, you get d over x is x squared plus h plus d over x squared, and multiply the numerator and the denominator by x, or multiply by x over x to get d over x squared plus h plus d over x, multiply by x over x again to get another factor of x on the numerator and remove the x squared from the denominator. So then you get tan theta is equal to x over x squared plus h plus d. And that's a pretty simplified expression as far as I'm concerned, and I'm happy to leave it like this for now. So tan theta is x over x squared plus h plus d. To be honest, out of the step 1 specimen paper, I thought this was one of the more straightforward questions, because it is not too demanding in any way, basically. It's just, it needs a little bit of creativity to get going, but once you've gotten going, it's not very hard at all. So, tan theta is x divided by x squared plus h times h plus d, which is this constant term here. If we differentiate tan theta, we get the differential of this expression, x over x squared plus h times h plus d. And we can differentiate one expression over another by using the quotient rule. The differential of u over v prime is u prime v minus uv prime all over v squared. So if we reserve a little space here, u is equal to x, u prime is equal to 1. V is equal to x squared plus h times h plus d, but v prime is just 2x because the constant term disappears. It doesn't vary with x. So this is, the differential is 1 times x squared plus h times h plus d minus uv prime, so minus 2x times x, v prime times u, all over v squared, all over x squared plus h times h plus d squared. Now, I would be worried about the fact that this is a pretty ugly expression, if not for the fact that the only thing I need to actually do with it is find when it's 0, in order to find all of the possible stationary points, all of the possible maxima, where in the values of x that we know could be taken, and that is, x could be anywhere from just above 0 to positive infinity. So if I just copy-paste that function there, we know that d by dx tan x is equal to this. I believe it is asking us to figure out, the value of x for which theta has its maximum value. I may have done something silly here. D by dx tan theta equals that. Let me figure something out. Okay, not all is lost. This is still a useful expression. So d by dx tan theta is h times h plus d minus x squared over x squared plus h times h plus d squared. Then what do we do now? We want d theta by dx. Oh, right, I realized what to do. So d by dx tan theta is equal to d theta by dx times d by d theta tan theta. And really, to maximize theta, we want d theta by dx to be equal to 0. So this is equal to h times h plus d minus x squared over x squared plus h times h plus d squared. And because d by d theta tan theta is sec squared theta. Let me just check that. Actually, do we need to do any of that? Because this is sec squared theta. It sort of doesn't matter what sec squared theta is, because as long as d theta by dx is equal to 0, then this whole left-hand side is equal to 0. And then the whole right-hand side must also be equal to 0 no matter what. So let's just say that d theta by dx were equal to 0. Therefore, 0 equals, or 0 times sec squared theta, which would be equal to 0. Or rather, Am I making any assumptions that couldn't really be made? I don't think so. I don't think so. 0 is equal to h times h plus d minus x squared over x squared plus h times h plus d squared. Yeah, because if sec squared were moved to the bottom, I just take sec squared theta to be 1 plus tan squared theta and work out the whole expression again. Oh, that may change things though. So I'm gonna actually work it out a little bit more. I'm not fully confident in taking that jump here. I'll just quickly check what happened. So if this goes to the bottom here as 1 plus tan squared theta, and this were equal to tan theta were x over x squared times plus h plus d. I've realized what happened. So the denominator here would be something over x squared plus h times h plus d, and that would move this factor, or this factor squared, up to the numerator. But if the numerator times this expression were equal to 0, the only expression that could possibly have a real x and still be equal to 0 is the original numerator. So we don't really need to care about whether or not this is equal to 0, because if it is, h times h plus d is positive, x squared plus positive equals 0, x squared equals negative, x is imaginary. So overall, we could have taken the shortcut that we had at the beginning. Although it is good that we checked this, because there is always the possibility that there were other values of x that made d theta by dx equal to 0, which we might have missed had we not done this check. But anyways, now that we know that if we let d theta by dx be equal to 0, then this fraction is equal to 0, or rather, the numerator is equal to 0, because for all real x creating real denominators, the denominator can never be 0. As x squared is always 0 or greater, and h times h plus d is always greater than 0. Or 1 over the denominator can never be 0 for any real denominator. So h times h plus d minus x squared would be equal to 0 if d theta by dx were equal to 0. And x squared would be h squared plus dh, and x would be root h plus dh, h squared plus dh. So that's one possibility for the maximum of theta. But then what? If theta is maximized, then this could happen if we put a graph here. What if the graph went like that, but just suddenly stopped here because x cannot be negative? X cannot be because x cannot be negative. Or what if it went like that to infinity, but because at positive infinity there were no more stationary points, and we couldn't actually see what theta became. Or we couldn't actually see if there was a maximum beyond the one stationary point that we did find. So in case this is the case, we need to check at the limiting conditions where x is equal to 0 or x goes to positive infinity, just to make sure that this is actually a maximum. Because the other way you could do this is by differentiating d theta by dx again, and I'm really not bothered when such a simple method exists. So give me a second, we're going to drink some water. Alright, I'm back. So when x is 0, what is theta? Well, tan theta is, let's see, when x is 0, tan theta is equal to 0 over h times h plus d, which is equal to 0. Therefore, theta is equal to 0. So we know the graph doesn't go like this, it goes more like this, to the origin. What about positive infinity? Well, you get tan theta, the limit as x goes to positive infinity of tan theta is the limit as x goes to positive infinity of x over x squared plus h times h plus d. And if we divide both sides by x squared, we get 1 over x times this over x squared plus 1 here. And because x is going to infinity, this goes to 0, this goes to 0, because both of these denominators go to infinity, and we're just left with a 1 here. So this is 0 over 1, which is 0 again. So the graph looks something like this, because it must be decreasing if there are no other stationary points on either side. And it goes to 0 from some positive real value. Therefore, this is the x at which tan theta is maximized. So the value of x is indeed root h squared plus dh. So that's all I have for this video. Hopefully it was a useful exercise to you to be able to see someone else solve this question if you had any trouble with it yourself. And remember, these questions are tough, they're designed to stretch you, and if you are someone who found it difficult, hopefully you learned something from this video, and hopefully the next time you see a question like this, you're armed with the tools you need to confront it successfully. Hopefully you understood this in a way that you could teach it to someone else if you needed to, and yeah, that's basically all I have to say on this. If you enjoyed the video, do subscribe, like the video, share it with your friends who may be in need of it, and until next time, thank you for watching.